Let's get started. After today, we only have 4 more classes. The last class is 2 weeks from today. So today and Wednesday, we're going to go through the details of the Morse index theorem, which I will remind you today what it says. I stated it last week. So the index form of a geodesic is basically the thing that appears as a second variation formula of the energy. It's a bilinear form, or equivalently a quadratic form, on the space of piecewise smooth vector fields along the geodesic. And the index form tells us something about the index of that quadratic form. So let me remind you exactly what it says. So we fix a non-constant geodesic, right? A is bigger than 0. This is a non-constant geodesic on M. And we look at the space of all piecewise smooth vector fields along gamma, which vanish at the 2 endpoints. Okay, that's an infinite dimensional vector space. And on this infinite dimensional vector space, we have the following symmetric bilinear form, which has an associated quadratic form. It's called the index form. This is the thing that when you plug in V and W, you get this: the integral from 0 to A of V prime inner product W prime minus R of V gamma prime W integrated over 0 to A. So this is symmetric in V and W. This one's obvious, and this one is symmetric in V and W by the symmetries of the Riemann curvature tensor. And this is exactly this is equal to the E double prime of 0 for, well, let me not write it. If you set V equal to W, you get a quadratic form, and that quadratic form is exactly the second variation of energy at time 0 for proper variations, right? We have these vector fields are 0 at time 0. Okay, and the index theorem says that what is the index of a bilinear form, a symmetric bilinear form? It's the dimension of the largest subspace of V on which this thing is negative definite. Now, for an infinite dimensional space, there doesn't have to be a finite index. So the first thing this tells you is that this index is finite. So there's not a well-defined unique maximal negative definite subspace, but any two negative definite subspaces which are maximal in the sense that they aren't contained in a larger negative definite subspace will be finite dimensional with the same dimension. And this index is equal to the number of conjugate points of gamma in the interior for t bigger than 0 and less than A, counted with multiplicity. So remember, a point is conjugate to the initial point of a geodesic if there exists a non-trivial Jacobi field along the restriction of gamma from the initial point to that conjugate point, which vanishes at the 2 points. Okay, and then we showed that happens if and only if that point gamma of t is a critical point for the exponential map, where the push forward of the exponential map becomes singular, and the multiplicity of that conjugate point was defined to be the dimension of that kernel. Okay, so there was some questions at the end of last class about why we're excluding A, but we have to be clear what we're saying here. This thing, if you think of this for fixed V and W as a function of A, then certainly this is continuous as a function of A. It takes values in the reals. But that's not what we're talking about here. We're talking about the index of this quadratic form. The index is integer value. But once we know that the index is finite, which we'll prove today, once we know it's finite, the index is a function which depends, like we can look at the index of I sub t, where I go from 0 to t, and that's what we're going to do. And that's a function from t to the non-negative integers. Right? It's not real valued. And it's very, very not obvious how that function depends on t. Okay, so what we're going to prove is that function, which is the index of I sub t, where I sub t is going from 0 to t, we're going to prove that takes values in the non-negative integers, it's finite, and that it's continuous from the left, and it's not continuous from the right. It has jump discontinuities from the right. It's a step function, okay? And the amount that it jumps at each step is exactly the multiplicity of each conjugate point. Okay, so this is the theorem.
Comment.
Yeah.
Yeah, so after I asked you that question, I just realized that even if you take like a constant times the identity matrix, that's non-singular unless the constant is 0. So for a non-zero value, it's going to have no kernel. For the 0 value, it'll have everything. Yeah. No, so it's just not continuous in the index. Like the dimension of the kernel is not.
the dimensions of spaces be, you can't just because you look at the quadratic form and there it depends on some parameter in a continuous way, that doesn't mean you can infer anything really about the continuity of the dimension of the kernel or the index or whatever. Okay. So we're gonna do this slowly. We're gonna build up a bunch of preliminary results. In the first half of the lecture, we're gonna get to the point where we're showing that the index is finite. At least the index, yeah, we'll show that the index is finite. And we'll also show, remember, this is a symmetric bilinear form, so it has a well-defined radical. The radical is the subspace on which it's degenerate, right? It's all the elements capital V in script V such that this thing vanishes for all W. We're going to identify exactly what that radical is. The radical consists of the Jacobi fields, which vanish at the two endpoints. And then we're going to prove the index is finite. And then eventually we're going to get to studying this function, the index of I sub t, and looking at its properties. So the first proposition is the radical of I sub a on this space V consists of the Jacobi fields along gamma that vanish at the endpoints. Okay, so everything in script V is a piecewise smooth vector field along gamma, which vanishes at the two endpoints. And we'll see that the ones that are in the radical are exactly the ones which are Jacobi fields. So that is, more precisely, V in script V satisfies that IA of VW equals 0 for all W, if and only if V is a Jacobi field. Okay, and we already know that the space of Jacobi fields, of all Jacobi fields along a geodesic, is finite dimensional. Here we're looking at possibly less of them, right? Because we want the ones that vanish at the two endpoints. So it's still going to be finite dimensional. This shows that the radical of IA is finite dimensional, right? Which it didn't have to be a priori. So let's see why this is true. So first of all, let's get a different formula for this index form. So on each subinterval tk minus 1 tk of 0a, where both V and W are smooth, let's do the following calculation. So first of all, let me remind you, script V is piecewise smooth vector fields, right? So they're only allowed to jump at a finite number. The derivative, the covariant derivative, is only allowed to jump at a finite number of places. So V, we can decompose the interval 0a into a finite number of pieces on which V is smooth, and same thing for W. And by taking the union, the common refinement of both of those subdivisions, I can assume that I've got a finite number of subintervals on which each of these are smooth. Then I can take d by dt of V prime W by the product rule, because the covariant derivative is metric compatible. I get this. So let me rearrange this because I want to rewrite this first term here. We've done this before, but we might as well do it again. So the integral from 0 to a, not 0 to a, yeah, 0 to a, V prime W prime dt, that's going to be the sum from k equals 1 to, let's say I have n of them. I'm rearranging this, I'm solving this. So I'm going to have the integral from tk minus 1 to tk of d by dt v prime w minus v double prime w dt. And in the second integral, remember v double prime is not defined, it's not well defined at the tks, right? But that's just a finite number of points. So this integral makes sense. So I can write this by the fundamental theorem of calculus. On the first term, I can just evaluate at the two endpoints. This is going to be the sum from k equals 1 up to n, v prime tk minus w tk minus v prime tk plus w tk minus the integral from 0 to a v double prime w dt. So these guys here, I'm just going to add up all the integrals. So what have I done here? The antiderivative of that is inner product of v prime with w. When I do it at the tk, I'm getting the left hand and I'm coming from below. So I get the left hand, and here I get, oh, this is tk minus 1. Right? And I can rewrite this because v of 0 and v of a are 0. I can rewrite this as minus the sum from k equals, let me put the integral first, minus 0 to a v double w minus the sum from k equals 1 up to n minus 1 of v prime tk plus minus v prime tk minus w of tk. And this is sorry because w vanishes at the two endpoints. Okay, so when k equals 1, this term isn't here, and when k equals n, this term isn't here, and then you see the other ones come with the plus sign has a minus. So that's what I've done here. We've had this formula before. So this is IA. Sorry, this is the integral from 0 to a of v prime w prime dt. And now I can write down IA of vw is going to be minus 0 to a v double plus r of v gamma prime w dt minus the sum from k equals 1 up to n minus 1 v prime tk plus minus v prime tk minus w of tk. Okay, I just added the curvature term. Where are we? Here. Okay, so this formula is going to be more useful for us for the purposes of proving this proposition about the Jacobi fields, about the radical. So let's also observe, before we continue, that now that I've written it in this form, you can see that all that matters is the points where v prime jumps, right? Because that's the only thing I have here. So without loss of generality, t0, which is t0, which is less than t1, tn minus 1 equals tn, which is a, are just the points where v prime jumps, right? Because to do this calculation, I subdivided where both v and w were smooth, but you can see that if there's a point tk where w jumped, w is continuous, right? If w jumped but not v, w prime but not v prime, I can just throw that one away. Okay, so there's the formula I want to use, and the reason we want to use this one is because the integrand now is exactly the Jacobi equation, the inner product of the Jacobi equation with w. So we want to show now that we're in the radical if and only for a Jacobi field. So suppose V is a Jacobi field in script V, that means it vanishes at the two endpoints. Then we know that V double prime plus R of V gamma prime is 0 on 0A, and V is smooth. Hence, IA of V W is 0 for all W, so V is in the radical of IA. You see, the integrand This guy is completely, oops, yeah, this guy is 0. So this whole thing vanishes and there's no jumps in the derivative. So conversely, this is just like how we characterize the critical points of the energy functional. Conversely, suppose V is in the radical of IA. This means that IA of the inner product W is 0 for all W in script V. Let H be a smooth function such that H of T is positive for all T not equal to the TKs, K equals 0 up to N, and H of TK equals 0, and let W of T be H of T V double prime plus R of V gamma prime gamma prime. So remember, this guy only makes sense away from the TKs because V double prime is not well defined at the TKs. But H here goes to 0 at the TKs. So this is a well-defined piecewise smooth vector field along gamma, and W of 0 equals W of A equals 0. So we're going to put that guy into the formula on the right. So 0 is equal to IA of VW. And notice also W of TK is 0 for all K. So when I put it in here, this term is going to drop out because I chose my W to vanish at each of those points. And then this is going to be minus the integral from 0 to A H of T times V double prime plus R of V gamma prime norm squared. Okay, and H is non-negative. So this thing is continuous and non-negative. This implies that H times V double prime plus R of V gamma prime squared is 0 on 0 to A. And that implies that V restricted to TK minus 1 TK is a Jacobi field. Right? Because H is not 0 away from the TKs, so this thing has to be 0, and that's the Jacobi equation. Now we're going to choose another vector field. Let U be in script V be such that U of 0 equals U of A equals 0, and U of TK is exactly this jump, K equals 1 up to N minus 1. So you can use bump functions to do this. And I ask you to do something like this on assignment 4. See assignment 4, question 1. Okay, so I'm not going to go through the details here. And then what do we get? We get 0 is IA of VU. And now we know that this function is 0 except for a finite number of points. So that doesn't affect the integral. This integral will be 0. It's going to be minus 0 minus the sum from K equals 1 up to N minus 1, VK prime TK plus, sorry, V prime TK plus minus V prime TK minus squared. And again, this is a sum of non-positive things equals 0. This means that V prime TK plus equals V prime TK minus. So there were no jumps to begin with. That means in this formula here, I don't have this term. I just have this. So the argument that I use to show that this vanishes in fact vanishes everywhere. So V has no jumps, V prime has no jumps. And this implies that V is a Jacobi field on 0A. Okay, so there's two steps, right? Now that we know that this isn't actually here anymore, this is just equal to this. And then you repeat the first step again, right? With W equal to this. Let me see, is that right? Double. I guess I still have to, all I know is that it's at C1. I don't know that it's in C2. So V is in C1, but V satisfies Jacobi equation on this, and that implies V is smooth, right? Because so once I know it's C1, then I can do this argument, except for the what am I doing? Right, there's no jump points anymore. So I get that this, wait a second. Oh, I'm a little confused to argue this. We've done this before though, so I can't remember exactly what the logic is. But these points aren't there, and therefore this still doesn't make sense at a finite number of points. I guess it's because it satisfies the Jacobi equation on, I mean, the way to argue it is it satisfies the Jacobi equation on 0, let's say T1, and then the solutions to the Jacobi equation are smooth. So it'll extend and then you keep going like that. So you can check the details. Let's not worry about that. Okay, so we've identified the kernel of this guy, sorry, the radical of this quadratic form as being the space of Jacobi fields, which vanish at the two endpoints, which is finite dimensional, and therefore the radical is finite dimensional. Okay. So corollary, there's several corollaries here that the Carmo just doesn't put any details in here, so I want to flesh them out. IA is degenerate, i.e. the radical of IA is not 0, if and only if gamma A is conjugate to gamma of 0 along gamma. And in this case, the dimension R of the radical equals the multiplicity of gamma of A as a conjugate point. And that's immediate because we just proved that everything in this radical, which is not 0, is exactly a Jacobi field vanishing at the two endpoints. So if V is in the radical, so not if, V is in the radical of IA and V not equal to 0, if and only if V is a non-trivial Jacobi field along gamma vanishing at the endpoints, and that's by definition the condition that gamma of A is conjugate to gamma of 0. And the multiplicity is exactly the dimension of the space of these Jacobi fields. Okay. So we've understood the radical of this bilinear form. That's well defined. But the index, once we show it's finite, is not, the number is well defined, but not the actual space. There's no unique maximal negative definite subspace. Okay, just the dimension is unique. So before we can get to the next step in our analysis of this bilinear form, we need to introduce some additional structure that's going to be, the results are going to be independent of this additional structure, but we need to introduce it as an auxiliary device. So this is typical in math, right? You want to prove something, you have to introduce some extra structure, and then it doesn't matter how you did that. So this is our geodesic gamma of 0, gamma of A. What we're going to do is the following. So since each point P in M lies in a totally normal neighborhood, remember a totally normal neighborhood is an open neighborhood, which is a geodesic ball of a certain radius, which is contained in a geodesic ball of a certain radius around each of its points. And since the image gamma of 0A is compact, we can choose a subdivision 0 equals T naught less than T1 less than Tn minus 1 less than Tn equals A of 0A, such that the image of gamma restricted to Tk minus 1 up to Tk is contained in a totally normal neighborhood. So for k equals 1 to n. So before I draw the picture, this is not the same subdivision as we had before, right? Before, it was for a fixed vector field v in script v. We looked at the places where that vector field could jump. Now there's no vector fields here. We're just fixing the geodesic, and we're decomposing the domain of the geodesic into pieces so that each one of them, let me draw. So maybe here's some totally normal neighborhoods. More colors. So I know that every point on the image of this curve lies in a totally normal neighborhood, and that said it's compact. I can cover it by finitely many of them, and because they're indexed by points on this curve, I can order them, right? So I can put them in order. So here, maybe this is T1. This is gamma of T1. This is gamma of T0. Gamma of T. Maybe this is gamma of T2, etc. So each of these segments from gamma of Tk minus 1 to gamma of Tk lies completely inside one of these normal neighborhoods. Okay, and that's because each of these points, I mean, this is the finite cover by normal neighborhoods. So in particular, each gamma restricted to Tk minus 1 Tk is minimizing. Right? That's because each of these segments lies completely inside a totally normal neighborhood. So this, for example, gamma of Tk minus 1 Tk, the image, well, this maps from Tk minus 1 Tk into the ball of some radius delta centered at gamma of Tk minus 1. Right? Because it maps into this totally normal neighborhood, which is contained inside a normal ball centered at each of its points. Okay, so therefore it's in the domain where the exponential
Just
map,
comment.
it's in a geodesic ball. Yes.
Yeah, I don't think
Yep.
the way you've drawn it, the way you've chosen your T, I don't think that's right, because you've kind of put a, you've covered the path with open balls, and then you've picked points in the intersections. So the ball
No,
isn't
I
really
didn't.
centered.
The ball is not centered at that. Remember what it means to have a
Mhm.
totally normal neighborhood. W is a totally normal neighborhood. Let me say W comma delta is a totally normal neighborhood, means that P is contained in B delta. I mean, it means that W is contained in B delta of P for all P and W, right? So for any point in W, I haven't drawn the B deltas. These aren't centers of geodesic balls, right? These are the
Mhm.
W's. I've covered it with a finite number of W's. And then you're right, I chose a point in the intersection of, I can order them, and I chose a point in the intersections. And then this guy, this pink ball is a totally normal neighborhood. So it lies inside the ball of radius some delta centered at this point. So it's in the domain of the exponential map, where it's in the domain, it's in a geodesic ball. It's contained inside a geodesic ball. Does that clarify?
Maybe I'm just not reading it correctly.
Okay, well, you can ask on Piazza or something. Let's just keep going.
Okay, yeah, carry on.
Okay, so each of these guys is minimizing because it's inside a geodesic ball. And therefore, and gamma restricted to TK minus 1 up to TK contains no conjugate points to gamma of TK minus 1 to TK. So you have to be very careful what I'm saying here, what I'm not saying here. I'm not talking about conjugate points of gamma. Conjugate points of gamma that means conjugate to the initial point of gamma. Now I'm restricting this to this closed subinterval, and that's a geodesic. And I'm saying that on this interval, there is no point, no time, which is conjugate along this geodesic to the initial point of this geodesic. And that's because this geodesic lies completely inside a geodesic ball. So the exponential map at gamma of TK minus 1 has no critical points inside that totally normal neighborhood. Okay, so this is because exp of gamma TK minus 1 is a diffeomorphism onto well, let me write it like this better. Gamma TK minus 1, this is what I wrote up there, is contained in some UK minus 1. This is a totally normal neighborhood, which is contained in some exp gamma TK minus 1 of some ball of radius, some delta. Okay. And gamma TK is also in UK minus 1. Okay. So we can do this. We can chop up our geodesic into a finite number of subdivision points such that the restriction to one of those closed subintervals is minimizing with no conjugate points to itself. Okay. So Do Carmo calls this a normal subdivision. The only word in math that's more overused than normal is the word Euler. So I don't want to call it normal because, especially in this course, normal you think means something to do with orthogonal, right? There's no, let's call it regular. That's also overused. But at least it doesn't confuse us with orthogonality, and it is hinting that somehow we've chosen this subdivision so that on each of these subintervals, gamma is as well behaved as can be. Okay, so now we're going to fix this. Gamma is our fixed geodesic. We're going to fix this subdivision once and for all. Fix such a regular subdivision for the rest of the day. Of course, it's not unique, right? There's lots of ambiguity here. And what I'm going to do is that using this subdivision, I'm going to decompose script V into a direct sum of two subspaces. And that direct sum depends on this choice of regular subdivision. But the conclusion that I want to prove, that the index is finite, is not going to depend, because the statement that the index is finite is independent of any subdivision of gamma. Okay, so we'll show, using this subdivision, that the index of IA is finite. And of course, the conclusion is independent of the choice. Independent of the choice of subdivision. And later, probably not today, probably Wednesday, when we actually show that the index function behaves the way we want it to behave, then we're going to be able to, we're going to argue that with all loss of generality, we can choose our subdivision in a way that has another nice property, but again, it doesn't affect the conclusion. Okay, so what's the next result? Let's define two subspaces of V using the subdivision and prove a direct sum decomposition. So recall, script V is the piecewise smooth vector fields along gamma such that V of 0 equals V of A equals 0. Okay, let's define two spaces. Define V minus. You'll see why it's called minus in a few minutes, in 10 minutes or so. This is the subspace of V consisting of elements capital V such that when I restrict to each of these subintervals, this is a Jacobi field. For all k equals 1 up to n. Okay, so notice V doesn't have to be a Jacobi field. Because these guys are only piecewise smooth, right? So a Jacobi field is smooth. So something in here, here's gamma, and here's these subdivision points that I've chosen. So it vanishes, these things vanish at the two endpoints, but along here it's a Jacobi field, and it's continuous because it has to be piecewise smooth, but along here it's also a Jacobi field, but from here to here it may not be a Jacobi field because it'll have a jump discontinuity in the derivative. Okay, so this is what V minus is, and this is clearly a subspace of V, right? Because this condition is preserved under linear combinations, and V minus is finite dimensional because each space of Jacobi fields along gamma restricted to tk minus 1 to tk is finite dimensional, right? For each of these restricted geodesics, there's a finite dimensional space of Jacobi fields there, and then I just have to take, I have a finite collection of finite dimensional spaces, and I have to patch them together so that they're continuous. So the elements of V minus are a subspace of this direct sum of the Jacobi fields along gamma restricted to tk minus 1 tk. right? They need to patch together to be continuous. You can write this in a more precise way, but it's just going to take long and we don't need to, right? So you can, the space of Jacobi fields along here, you take the abstract direct sum of finite number of finite dimensional spaces. That's a finite dimensional space. And then there's a subspace of that. So it has to be finite dimensional, which is V minus. So I've defined a particular subspace there. I'm going to define one more, which I'm going to call V plus. Define V plus to be the subspace of V consisting of those elements V such that they vanish at these partition points. Okay, this is also clearly a subspace because this condition is preserved under linear combinations, and it's infinite dimensional. That's easy to see, right? Because just the space of piecewise smooth vector fields that vanish at T0 and T1, that's already infinite dimensional, and then I can just let it be zero everywhere else. So it's infinite dimensional. And then the proposition we want to prove is that this gives us a direct sum decomposition of V with some additional structure. So here's the result. V is V plus direct sum V minus, direct sum decomposition, moreover, if V is in V plus and W is in V minus, then IA of VW is 0. So the way Do Carmo phrases this part is he says that these two summands are orthogonal with respect to the symmetric bilinear form, which is a perfectly fine way to say it, but I don't want to use that language because I don't want us to get confused with the inner product, because this bilinear form is not positive definite in general, right? So this is not it's a symmetric bilinear form, but it might not even be, it won't even be non-degenerate in general, right? It'll be degenerate. So if you take something in V plus and something in V minus and you plug them both into IA, you get 0. And finally, the restriction of IA to V plus is positive definite. So before we prove this, I just want to emphasize these guys are not unique, right? They depend on that subdivision I chose, that regular subdivision. And now you see why I called this one V plus, because the restriction of IA to V plus is positive definite, and you'll see why the other one is called V minus in a minute. It's not, we're not saying that the restriction to V minus is negative definite. That's not true, because there's a radical as well. Right? If I had written V as a direct sum of two subspaces, one on which is positive definite, one on which is negative definite, then it's easy to see there wouldn't be a radical, right? So it's not going to be true that the restriction to V minus is negative definite. Okay. So let's see how this works. We're going to use the properties of this subdivision. Okay. So let's let V be in script V and let W be in V minus. So recall them, this means that W restricted to TK minus 1 TK is a Jacobi field. Okay, so sorry, let V be in W and let W be in here such that W of TK equals V of TK for all K equals 1 up to N minus 1. Why can we do this? This is where we use the properties. Because gamma restricted to tk minus 1 tk has no conjugate points. So we proved a long time ago, at the end of chapter 5, when we were looking at properties of Jacobi fields, we proved that if you have a geodesic on a geodesic segment with no conjugate points, then there exists a unique Jacobi field given the boundary conditions. And we proved earlier that there exists a unique Jacobi field along gamma restricted to tk minus 1 tk with given boundary conditions. This was the end of chapter 5. Okay, so I know that W is in V, so it has to vanish at 0 and at A. And this one, I started with some vector V and script V. So I'm choosing W and V minus. What is V minus? It's the things that are Jacobi fields along each of these things, right? So I can prescribe the boundary data, and that's what I'm doing, and I'm making it equal to V. Then V minus W is in V plus, because V minus W of TK is V of TK minus W of TK is 0, right? And that's what it means to be in V plus, that it's the vector fields that vanish at those TKs. So hence, V is equal to W plus V minus W, and this guy's in V minus, and this guy's in V plus. So V equals V plus plus V minus. I've written everything in script V as a sum of something in V plus and something in V minus. Suppose U is in the intersection, okay, then U restricted to tk minus 1 tk is Jacobi along gamma restricted to tk minus 1 to tk. And that's because it's in V minus, and it's in V plus. That means U of tk minus 1 equals U of tk equals 0. But by this remark here, there exists a unique Jacobi field given boundary conditions. So that means that this has to be 0. This is U equals 0 on tk minus 1 tk. And of course, that's true for all k. So hence, U is identically 0 on 0 to A. So V plus intersect V minus is trivial. So V is the direct sum of V plus and V minus. Okay, that proves the first of the 3 statements. So now let X be in V plus and Y be in V minus, and let's compute IA of XY. Remember, we had this formula for IA, X double plus R X gamma prime Y minus the sum hang on, I have to be careful. X prime TK plus minus X prime TK minus Y of TK. So remember, this formula was the TKs in this formula were the places where X can jump. But X is in, sorry, I did this wrong. X is in V minus, X is in V plus. This means that X restricted to TK minus 1 TK is Jacobi, right? So it's smooth on here. So this partition of the T's, which was given for just a particular geodesic, right? We had no vector fields. We fixed our geodesic and we chose this partition. By the definition, of V minus, everything that's in V minus is piecewise smooth with the jumps at those same TKs, right? Because this guy is smooth on each of these things. So therefore, the T's that are in this formula from earlier today are the same as the T's that we had before. And now this part is 0 because X is Jacobi on each of these subintervals. So this expression is 0, except for a finite number of points where it doesn't make sense. And then, so that integral is 0. And this is 0 because Y is in V plus. So Y of TK is 0, right? And that's exactly what motivates the definition of these two spaces. It's exactly so that we can see that they vanish. You know, if I take one guy in V minus and one guy in V plus, they'll vanish for different reasons, right? This part will vanish because X is in V plus, and this part in V minus, and this part will vanish because Y is in V plus. Okay, so IA of XY is 0. That's the second part of the statement here. And the last thing that we have to show is that if we restrict it to V plus, we get something positive definite. So it remains to show that IA restricted to V plus is positive definite. Okay, so now you notice we've used twice in this argument, we use the fact that gamma has no conjugate points on the subinterval, right? So that we know that there's a unique Jacobi field with prescribed boundary data. We haven't used the fact that it's minimizing on each of those subintervals. So this is what we're going to do it now. So since gamma restricted to TK minus 1 TK is minimizing, it has less energy than any other path between its endpoints, because remember, for geodesics, those are parameterized proportionally to arc length. Minimizing the energy is the same as minimizing the length. So hence, the integral from TK minus 1 to TK of V prime minus R of V gamma prime V dt is greater than or equal to 0, because this is the second variation formula. Right? If I look at another curve, here's gamma of TK, gamma TK minus 1 to gamma of TK. This is minimizing. So if I do a variation with a proper variation, the energy can only increase. So this is a local min, and therefore the second derivative is non-negative. Okay, so adding them up from k equals 1 up to n, what do we get? When I add all these up from k equals 1 up to n, I get IA of so whenever V is the variation vector field of a proper variation of gamma restricted to TK minus 1 up to TK. Okay. So now adding them all up, I get that this is greater than or equal to 0 for all V in V plus. Because remember, what was V plus? V plus was just the piecewise smooth vector fields that vanished at each of the TKs, right? So if it vanishes at each of the TKs and I restrict it from TK minus 1 to TK, then it's the variation vector field of a proper variation. So this part will be non-negative, and I'm adding them all up. So this is since V of tk is 0 for all k. Okay, so what have I shown so far? I've shown that it's non-negative. IA is non-negative on V plus. Okay, so IA of VV is greater than or equal to 0 for all V in V plus. We're halfway there. Let's call this star. So we still have to show that IA of VV is positive for all V not equal to 0 in V plus. That's what positive definite means. Okay, so suppose V is in V plus and IA of VV is 0, we need to show that V has to be 0. And we'll be done. Okay, well, let's write W as W plus and W minus. This is the decomposition, V plus and V minus. Right, we've shown that this directs some decomposition. So if I take any W in script V, it has a W plus and a W minus. These are unique. And this part, if I take IA of VW, that's going to be IA, it's bilinear, VW plus and IA of VW minus. So this is 0 since V is in V plus and W is in V minus. We just proved on the previous board that if you take one in V plus and one in V minus, you get 0. So let's see where I'm going to use this. And now, by star, for all lambda real numbers, if I look at IA of V plus lambda W plus, V plus lambda W plus, this is greater than or equal to 0. Because V was in V plus, and W plus is in V plus, and that's a subspace. So this is in V plus. So this is non-negative. But let's expand this. This is equal to IA of VV plus 2 lambda IA of VW plus lambda squared IA of W plus W plus. And this one is also non-negative because by star. Okay, so what do I have? And this one is 0 by hypothesis. Right, I'm assuming IA of VV is 0. So what do I have? I have 2 lambda B plus lambda squared A squared. A is greater than or equal to 0 for all real lambda, where B is IA of VV of VW plus, and A is IA of W plus, and this is at least 0. Okay, so suppose if A is 0, then I get lambda B is greater than or equal to 0 for all lambda. The only way that can happen is if B is 0. Okay, if A is not 0, it's not negative, so it's positive. Then what do I have here? A and B are fixed. A is positive, and B is some real number. And this is a quadratic polynomial in lambda, which is always non-negative. We get A lambda squared plus 2 lambda B greater than or equal to 0 for all lambda. Well, that implies the discriminant has to be non-positive, right? There's no distinct real roots. So that means 4B squared is less than or equal to 0, and that means that B is equal to 0, right? So regardless of what situation we're in, B is equal to 0. So IA of VW plus has to be 0. And then, because I already know that this one is 0, now I know that this is also 0, we get that IA of VW is 0 for all W. Okay, but now that means V is in the radical. Therefore, it's a Jacobi field from the previous proposition. So V is in the radical of IA, implies V is a Jacobi field along gamma. But V of TK is 0 for all K. Remember, V was in V plus. So V is identically 0 on 0A, which is what we wanted to prove, right? We wanted to prove that if IA of VV was 0, then it had to be 0. So why is this? This is, again, what we did a few minutes earlier, right? Is because we chose this subdivision so that on each restricted geodesic, the Jacobi fields are unique given the boundary data. And since the boundary data is 0, it has to be 0. Okay. Any questions about this argument before I do a corollary to this? So I want to emphasize this choice of decomposition is very arbitrary, right? I mean, there's a lot of freedom, and therefore the V plus and the V minus depend on that choice. And so they're far from unique, they're far from canonical. But the radical is certainly canonical. But then the next corollary that Do Carmo states without proof is, again, something that's not obvious unless you are very familiar with working with bilinear forms on infinite dimensional vector spaces. So I really want to put in the details. It's the following. First of all, the index of IA is equal to the index of the restriction of IA to V minus. In particular, the index is finite. Because once we've proven this first sentence that the index is equal to the restriction of the index to here, that's a finite dimensional space. And on a finite dimensional space, of course, the maximal negative definite subspace is finite dimensional. Remember, this was part of the Morse index theorem. We've already proved, well, once we finish this corollary, we'll have proved that the index is finite. And what will remain to prove is the value of the index. And similarly, the radical of IA equals the radical of the restriction of IA to V minus. Okay, so that tells you that the radical is finite dimensional, but we already knew the radical was finite dimensional. We already knew the radical was finite dimensional. So that doesn't give us that much new information. Okay, so let's see why this is true. So we know that V is equal to V plus V minus, and IA is positive definite on V plus. Okay. So let's suppose that V is in the radical of IA. What does that mean? It means that IA of VW is 0 for all W in V. We can write V as V plus V minus. So we get 0 is equal to IA of V plus V minus with W. And that's equal to IA of V plus W plus IA of V minus W for all W. Okay, so let's just take W to be V plus. Then this part is going to be 0. We get 0 is IA of V plus plus IA of V minus V plus. This is 0. And here it's positive definite. That means that V plus is 0. So V is actually equal to V minus, is in script V minus. So the radical of IA equals the restriction of, it equals radical of restriction of IA to V minus. Okay, so this shows that if we're in the radical of IA, then we're actually in V minus. And because this holds for all W, it holds also for the W's that are just in V minus. Okay, so that's the second part of the statement. Now the first part is the more interesting part. And again, Bill Carmel says nothing here. He just doesn't even think it's worth any mention. Okay, so for the first part, let's let K be a maximal negative definite subspace of V. So we know that there exists such a thing. It might be 0, right? Because on the 0 space, of course, everything is positive. Every bilinear form is positive definite and negative definite on 0, because there's no the situation, the condition is satisfied vacuously. Right? There are no non-zero vectors. So then you can just say, let's take how does it work? You can look at, yeah. Anyway, there's some standard argument for showing that such a thing exists, but it may not be finite dimensional, right? We need to show K is finite dimensional, and that the dimension of K equals the index of IA restricted to V minus. That's what the first part of the proposition says. Okay, it's not true that K must be a subspace of V minus. So there are going to be lots of negative definite subspaces of V. Some of them are going to be in V minus, some of them are not, but they all have the same dimension. Okay, so and sorry, what did I say? Not negative definite, maximal negative definite. Right? Some of them are going to be in V minus, some of them are not. So how are we going to show this? Define a linear map T, which is going to go from K to V minus by V, which is V plus V minus, is sent to V minus. So it's just the restriction of the projection V plus V minus to V minus to the subspace K. Okay, so this is certainly linear. Of course, this is not an orthogonal projection. There's no inner product here at all. This is just a direct sum decomposition. So this is a linear map. We're going to prove two things about this linear. We're going to prove that it's an isomorphism. I mean, it's injective, sorry. So claim the image of, let's call it T, is a negative definite subspace of V minus, i.e. a negative definite subspace of IA restricted to V minus. Okay, so let's see why that's true. Let V minus be in the image. With V minus not equal to 0. Let V be V plus V minus. So V is not equal to 0, right? Because this is a direct sum decomposition. The only way V will be 0 is if both components are 0. So if this component is not 0, this is not a 0 vector, then IA of V minus is equal to IA of VV minus IA of V plus. This uses the fact that IA of V plus and V minus is 0. Okay, so you just expand this. You put V as V plus V minus, expand both sides, and then bring it over. And then this is less than or equal to IA of VV, since IA restricted to V plus is positive definite, right? I don't know that this is strictly positive because I don't know that V plus is 0. V plus may be 0 or non-zero, but this is non-negative. So I'm subtracting something non-negative, so this can only decrease. And then this is less than 0 since V is not equal to 0 and sorry, this is in K, right? Which is contained in V. And K is a negative definite subspace. Okay. So that means that so V minus equals T of V non-zero in T of K implies IA of V minus is negative. So TK is a negative definite subspace of V minus. And the next claim is that T is injective. Well, if T of V equals 0, that means that V equals V plus, which is in K, and V plus, right? Because V plus is in V plus, and the V is in K. So this says that IA of VV is greater than or equal to 0 since V is in V plus, and it's less than or equal to 0 since V is in K. Therefore, it has to equal 0. So IA of VV equals 0, but V is in V plus. This means that V equals 0 because IA was positive definite on V plus. So kernel of T is trivial. So hence, K goes to T of K is a linear isomorphism. And T of K is in V minus, and T of K is negative definite. Okay, so I haven't used the maximality here, but you see that there's an isomorphism. If I have a negative definite subspace of V minus, then of course it's also a subspace of V and it's negative definite. but I went the other way. If I had a negative definite subspace of V, then I produced a negative definite subspace of V minus. And you can see that if I had maximal, it would take it to maximal because, I mean, otherwise, if there was a bigger one, then I can do this operation to get a bigger one on the other side. So the negative definite subspaces of V correspond to negative definite subspaces of V minus under this correspondence, and I can put maximal. Right? What we've shown is that any negative definite subspace of V is isomorphic to a negative definite subspace of V minus. And that means it's finite dimensional. And so the index of IA equals the index of the restriction of IA to V minus, which is finite. Okay. Oh, any questions about that? Yeah. Okay. So I didn't want to. Let's put in the details because I only have 5 minutes. Okay. Yeah, it's bad to say that they're correspondence because the map depended. No, the map depends on this decomposition. Yeah. So I shouldn't say there's a correspondence. Okay. So let's put in the details. Thank you. So suppose K is negative definite subspace of V. That implies TK is negative definite subspace of V minus. Okay, and hence finite dimension. Okay, but K has to be the same dimension. So K is finite dimensional, right? Because they're isomorphic. Let me erase this. And then how do we do with the maximality? Now let K be let K be a maximal negative definite subspace of V minus. This exists and it's finite dimensional because V minus is finite dimensional. Okay, so K is a negative definite subspace of V. If there exists K tilde properly containing K negative definite, then T of K tilde properly contains T of K is negative definite subspace of V minus, and that's a contradiction because K was maximal. Does that make sense? Okay, that's more precise. Okay, so I think we should stop, but let me just recall. So far, we've proved that the index of IA is finite, which was non-trivial. It remains to show next time, and it won't take the whole time, it'll probably just take half the lecture. Next time, that the index of IA equals the sum counted with multiplicity of the number of conjugate points to gamma in the open 0A, the interior conjugate points. Okay, once we do that, and we're gonna study this function, right? We know now that the index, so A here was arbitrary, right? I can do this for any A. So if I look at IT of VW, which is the integral from 0 to T of the usual thing, then I can look at the index of IT, and that's going to be a non-negative integer. Okay, So this function, it's a function that I will go from 0a to the non-negative integers. I of t is the index of it. We're going to look at this function. We're going to show that it's continuous from the left. It's not continuous from the right. It has a jump discontinuity, and the amount of the jump is exactly the multiplicity of the conjugate point. Okay, so we'll do that on Wednesday in the first half, and then we'll do a couple of quick corollaries of that. One of the corollaries is a different proof of what you're, well, almost the same proof, but much more roundabout way to problem 1 on assignment 4. Okay, there's a much faster way of doing problem 1 on assignment 4 because you don't need any of the chapter 11 material, right? You only need the chapter 9 stuff. So that'll be one corollary. And then after that, I think we're going to move on to chapter 12, which is about Priceman's theorem, something about the fundamental group of a manifold and geodesics that represent classes, homotopy classes in the fundamental group. So we have 4 more lectures, and I think we can, well, we definitely finish this in the first half of Wednesday, and I think we can finish chapter 12. We probably can't do chapter 13. Well, we certainly can't do all of chapter 13. We'll see if we say a little bit about it, or if we don't say anything at all, right? Because we're probably all tired. This is the first time I've had to use a 1.5-inch binder for a course. So you guys should be proud of that.